Okay, all right. Let us begin this session number 11. So this is the second last tutorial session for this course. And in this session, we are going to solve problems based on the power distribution automation and a smart grid. We will also solve problems based on the PV energy conversion system and wind energy conversion system. So let us begin with this first, a very simple problem. The first question is that in the wind turbine, the efficiencies of gearbox and turbine generator set are 70% and 95% respectively. So the in the wind energy conversion system, we are having the gearbox box efficiency and turbine generator efficiency are 70% and 95% given respectively. So determine the maximum theoretical overall power conversion efficiency of the unit. And the options are shown as. So all of you try it and then we will see the solution. So we know that in a wind energy conversion system, whatever the power available in the wind, we cannot extract fully from the wind. So there is a power coefficient term and then that depends on the rotor design and the tip speed ratio. So the maximum value of CP, the power coefficient comes from the Watt's law. So you have to use that maximum power coefficient term and the efficiencies of gearbox and turbine generator are given and you need to multiply all these efficiencies to get the maximum theoretical overall power conversion efficiency. We can write that power extracted by wind turbine is equal to power coefficient multiplied by the power available in the wind. We can denote it as PT is equal to CP into P naught. This is the usual notation. So from Watt's law, the maximum value of power coefficient is that maximum value of power coefficient is equal to 0.59. CP max. This we should know so that we can find the maximum theoretical efficiencies. This we need to remember. Another efficiencies are given below like this given values are efficiency of gearbox It is given as 0.7 or 70%, and efficiency of turbine generator is given as 0.95. Then we have maximum efficiency will be Cp max multiplied by efficiency of gearbox multiplied by efficiency of turbine generator. So this will be 0.59 into gearbox is 0.7 and turbine generator is 0.95. So all these comes as 0.39235 or 39.235%. So option B is correct. So if you have any doubt, then you can ask. Now moving to the next problem. The next problem is that from solar PV conversion system, a solar PV panel of rated 30 watt 10 volt. So each solar panel is of rating of 30 watt and 10 volt is to supply a 240 volt single phase load of 2.88 kilowatt. How many panels will be required for this and the arrangement? You have to tell the number of panels required and the what is the arrangement in series or parallel, how they will be connected. So from the load we can say that we are having load of 240 volt. Then from 280 volt we can find the number of series connected solar panels, because each solar panel having voltage rating is given, and that will sum up after summing of all the individual solar panel voltage rating, that will give equals to the 240 volt. You can if you have solved this problem, then you can type your answer in chat box, so I can see. For 2 volt 240 volt load, we can say that number of series panels required will be number of series panels will be 240 divided by volt per panel, voltage rating of per panel. 240 divided by each voltage of each of 10 volt rating. So 10 volt, this will be give you 24. Then first comes out as that 24 panels we have to connect in series. So only B and D options are coming. Now from the power rating or current rating, current required for the load, we can find out the parallel paths. So either way you can use the current or current required or power required for the load. Either way you can calculate. So I am using by this power method. So first we will find the current supplied by each panel. Current supplied by each panel will be power rating of panel divided by volt per panel. So 30 watt divided by 10 volt, it will be 3 ampere. So we can calculate the power produced by 24 series panels. Power produced by 24 series panels will be 240 volt is the voltage multiplied by current, then 720 watt. So from here we can say that number of parallel paths required is number of parallel paths will be total load divided by 240 s, that is power produced by 24 series panels. Total load is of 2.88 kilowatt. So 2880 watt divided by 720 watt will come as 4. So we are having 24 panels in series, and that all 24 panels in series connected, and we required 4 parallel paths each. So final answer will be 24 series panels and 4 such parallel paths, and 4 such parallel paths. Then only one option will come out. D is only matching, so D will be the correct. Pedro, you are correct. D is the correct option. Very good. So let us move to the next problem. So the third problem is that it is very nice problem. So a wind turbine has cut in a speed, rated a speed, and shut down a speed of 8 kilometer per hour, 35 kilometer per hour, and 50 kilometer per hour respectively. In which of the following wind speed it will have the highest generation? So you have given three wind speeds, that the characteristics of wind power generation. It will come from the power curve. So from there you have to tell that which speed it will be having the highest generation. So cutting speed of wind turbine is 8 kilometer per hour, and rated speed is 35 kilometer per hour, and then shutdown speed is, it is also called furling speed or cutoff speed, and shutdown speed is 50 kilometer per hour. So based on this data, you have to tell that in which of the flowing wind speed the wind turbine will have the highest generation, highest power output. So what do you all think? You can comment in the chat box. You can speak also if you want. There today not that much attendance, only two attendees are there. So if we see the power curve for the wind generation for wind turbine, we are having typical power curve of wind generator is like that. So this is the cutting speed, this is the minimum speed above which the wind turbine starts generating power. And between cutting speed and rated speed, power output is proportional to the proportional to the cubic of wind speed. So for this, between the cutting speed, power output from wind turbine is proportional to the cubic of wind speed. And after we reach this rated speed, at begin the rated power output. So we attain the rated power output, and until this shutdown speed, we are getting this rated power only. So whatever we can say that we can get the maximum power output between the rated speed and shutdown speed. This is the maximum power limit, that is rated power, it is defined. So we are getting this maximum power output between rated speed and shutdown speed. So rated speed is 35 kilometer per hour and shutdown speed is 50 kilometer per hour. So 35 and 50 kilometer, whatever it comes between, that all will be the correct answer. If 35 and 50 are given, then that will be also correct. So only one option is matching here, 45 kilometer per hour. So C option is correct. Cutting speed, somewhere it is also called as minimum speed. It is the minimum speed above which the wind turbine starts delivering power output. And the shutdown speed, there are so many names like shutdown speed having cutoff speed, cutoff speed, or furling speed. Or it you can say maximum speed. It is also called as maximum speed. The it is the maximum speed ever which we need to stop the wind turbine, or we have to change this some configuration like high pitch position. We have to turn it into high pitch position. So let us move to the next problem. You can also write here, it is one point that will be beneficial for understanding. Highest generation, highest generation is in between the rated speed of wind turbine and the shutdown speed. So the next problem is that the flowing form of storage is having the highest capacity and energy storage. And the options are lead acid battery, lithium ion battery, pump storage unit, and high power flywheel. So you can give your answer in the chat box. So I am giving you this plot so that it will be helpful for deciding this which form of storage having the highest capacity and energy storage. From this figure, you can clearly say that this pump hydro CAES are having the highest capacity waste energy storage system. What do you mean by this CAES? CAES is compressed air energy storage. Compressed air energy storage. And this SMES lies here in between this 10 megawatt. So SMES stands for superconducting magnetic energy storage. C. Yes. C is the correct option. Yes, both Petro and Jignesh, both of you are correct. If you see this figure, this pumped hydro having the highest capacity of power handling and this highest energy storage device. So this one is the correct option. Pump storage hydro unit. So whatever this lies in the first piece power quality beneath that the lowest point, they are all having higher power density that are useful in power delivery during transient condition. And whatever lies in this energy management, bulk power management, the top one, all are having higher energy density. So these are used to power delivering during the steady state time. So that is the difference. If you see this supercapacitors, lithium ion battery, all lies flywheels, all lies this during higher power, higher power density based energy storage devices, and that deliver power during the transient condition. And this high power density, the response is faster, and for this higher energy, those energy storage devices having higher energy density are having slower response. Now let us see the next problem. The fifth one is that a fuel cell needs. Now this is multiple select question, so more than one options can be correct. Multiple select question. So a fuel cell needs hydrogen supply at the anode side, or B, the hydrogen supply at the cathode side, C, the oxygen slash air at the anode side, D option is oxygen air at the cathode side. So for this you need to refer this figure. So at the anode we are having fuel in, or that is H2 hydrogen supply, and this air in, that is at the cathode side, or oxygen. So you can easily say the what is should be the correct option. So hydrogen at the anode side, then A will be correct, not at the cathode side, and oxygen at the cathode side. So D will be correct. A and D are the correct options. Now let us see the next problem. Next problem is that tip speed ratio of a wind turbine depends on, and the options are wind speed, rotor radius, and all of these. You can type answer in the chat box. If you see the definition of tip speed ratio, then we know that it is the relative speed of rotor tip with respect to velocity of wind. So tip speed ratio, we also say it as TSR or lambda. Tip speed ratio or lambda is the relative speed of the rotor tip with respect to wind speed. With respect to wind speed. TSR or lambda, it is the ratio of rotor tip speed or it is also called a tangential speed of rotor divided by wind speed. This one is also called a tangential speed of rotor. So we can say that tangent rotor tip speed, we can define it as r omega. R is the rotor radius, omega is the rotor speed in radian per second, and wind speed you can say u naught, free wind speed that is given as. So here omega is rotor speed in radian per second. We will see problems based on this tip speed ratio. So that here I am just defining the term in well manner. Rotor speed in radian per second, and then this r is rotor radius. If you want to convert it in this revolution per minute or revolution per second, then you can say it as omega is equal to r into 2 pi n divided by u naught. Then n, here it is rotor speed in rps, revolution per second. And you can also write in revolution per minute, then 2 pi n divided by 60. So 60 u, then n will be rotor speed in rpm, revolution per minute. So whatever in the question asked, based on that you can reply. So here we can see that T plus speed ratio wind turbine depends, sorry, yes, so it depends on wind speed also, and it depends on rotor radius also, it depends on rotor speed also. Then D is the correct answer. All of these is the correct answer. Now for from here we will see some few theoretical questions only, and then after that we will having numerical type question. So moving to the next problem. Next problem is that optimal network reconfiguration is a part of the flowing smart grid initiative, and the options are substation automation, B is distribution management system, C is distribution system monitoring, D is none of these. You can give your answer chat box. Yes. For last problem, D is the correct. Yes, Petro, you are correct. Very good. Now we having this problem number 7. So this is not optimal network reconfiguration does not comes under this substation automation. Substation is different part, and this monitoring also does not. This reconfiguration does not count into that. So only management part will comes under this. So distribution management system is the correct answer, and I have that is discussed in the class. So if you having see that how what is encounters under this distribution management system, we are having so many things for detection, isolation, and service restoration. This topology processor and this optimal network configuration also comes under this distribution management system. Integrated volt var control, switch order management, dynamic load modeling, load estimation, dispatcher training simulator, short circuit analysis, relay protection coordination, optimal capacitor placement, optimal voltage regulator placements. All these things comes under distribution management system. So moving to the next problem. Next problem is that the implementation of automated metering infrastructure needs. This is multiple select question. More than one options are correct. So you give your answer in chat box, or you can s- speak also, whatever method you want. And the options are a smart meter, B is bidirectional communication system, C is unidirectional communication system, D is none of these. So of course this is very simple. Automated metering infrastructure requires what? Of course it needs a smart meter that log data and communicate through the utility. So this comes under a smart meter is correct choice, and bidirectional communication system is also required. There should be bidirectional communication between the utility and customers, not unidirectional communication system. So both A and B are correct. Unidirectional communication is not correct. So A and B are the correct choice. For theoretical type question, we will move faster. Next problem we have, it is also simpler one. Smart meter will enable the efficient management of, and the options are bidirectional flow of power. B option is bidirectional flow of data. C option is bidirectional flow of power and data. D option is none of these. So you can type answer in the chat box. Yes. For last problem A and B are correct, and for yes, for last problem A and B are correct. Now for this ninth number problem, both should be there. This smart meter enables both efficient management of data and power. That means bidirectional flow of power and data. C is the correct. So let us see the next problem. Next problem is that supervisory control and data acquisition includes a SCADA system includes. A option is a smart control station. B option is sensors, analog, digital and digital analog converters. C option is bidirectional communication links. D is all of these. These type of problems will you have in this final exam. So try to solve, and whatever you think you should reply. Yes, D. Yes, D is the correct. All of these are should comes from this SCADA system. These having master control stations. We are having sensors, ADC and DAC are there, and bidirectional communication links are also required. So overall, all of these is the correct answer. Now we will solve these numerical type problems based on the wind energy conversion systems. So this problem says that the wind speed at the height of 10 meter is 5 meter per second, and the location is on land. The wind turbine location is on land, and A is given as this friction or roughness coefficient 0.14. Calculate the wind speed at a height of 40 meter. Sorry for interruption. So you all try and just So according to Wind Meteorological Organization, this standard wind speed is taken at a height of 10 meter. And if we estimate this wind speed at height h is given by the formula according to Wind Meteorological Organization standard wind speed mu naught is generally taken as generally taken as 10 meter from the ground. Now for this estimation of tower, wind power generation from by the height from the height of tower, we can say that estimated wind speed is estimated wind speed at height h is given by u is equal to u naught h divided by h naught power a. So this is the expression. You can also say that from here that wind speed at height h, you can say that it is proportional to h by power a. In this we are having given where u is wind speed at height h and this a is the roughness or friction coefficient. And u naught is the difference wind speed at height h naught. Using this formula you can find the answer for this question, so please try. U naught is the difference wind speed at reference height h naught. So for u naught is given as 10 meter 5 meter per second and reference height is given as 10 meter. So all values we are having given. Generally good sites having this low values of roughness of friction coefficient, and in general rule a taller tower is expected to result in higher wind speed than shorter wind turbines. So all values are given. We need to find this u naught is given as 5 meter per second. H naught is given as 10 meter, H is given as 40 meter. We have to find U. So U will be U naught is 5 meter per second and H is 40 divided by 10 and A is given as 0.14 meter per second. So 5 into 4 by power 0.14 will be the final answer. So if you do that, then you will get 6.07 meter per second. This is the final expression. So C is the correct answer. So from this relation we can tell that what will be the impact of height on the wind speed. Yes, Pedro, you are correct. Very good. 6.07 is the correct answer. So in this problem we have estimated the wind speed from the height of tower. Now will we estimate the wind power at a certain location by solving the next question. So moving to the next problem. This is having similar and this is having the same common data for four questions. So the data is given as a wind energy system has the following parameters. Rotor turbine diameter is given as 37.5 meter. D is given as 30.7.5 meter. Wind turbine maximum power coefficient is given as 0.38. Cut-in wind speed is given as 5.4 meter per second. Rated wind speed is given as 9.7 meter per second. So we are going to use this speed because we know that we are getting the rated power output at this speed. So cutoff speed we are not going to use because it is the maximum speed after which we need to stop the wind turbine. Air density is given as 1.225 kg per meter cube. Synchronous generator rated power output P to 200 kilowatt. That is final electrical power output is given as 200 kilowatt. So in the first part, in the 12th problem, it is asked that calculate the available power in the wind at rated wind speed P naught. So it is asked that available power in the wind at the rated wind speed. So we need to find this at rated wind. So we have to use this rated value. So if we write in the terms of mass flow of wind, then we can say that m dot dm by dt, then it will equal to rho a u naught, and this power available in the wind, that is p naught through an area A through an area A at a speed of free wind available in wind P naught through an area A at a speed of free wind U naught is given as, we can say that P naught is equal to half m dot U naught square. So this will be half rho A U naught square. Final expression will be rho half rho A U naught Q. This P naught will be half rho A U naught Q. So we need to remember this formula. We need to remember this expression. This one is very important. So here we requires what values? Given values are rho. We require rho. Rho is given as 1.225 kg per meter cube. We require A. A you can find from this rotor turbine diameter. We know that pi r square. So it will be pi d by 2 whole square. So pi 37.5 divided by 2 whole square. And then U naught is given as, that is rated wind speed, 9.7 meter per second. Then put all these value in P naught. Then we are having half rho is 1.225, then pi into U naught Q. U naught Q is 9.7 Q. Then doing all this, you will get 61,740.76 watt. I think there is a mistake. So what value you got? Anyone reply? 9.7 into pi into 1.225. Yes, there is a mistake. It will be 61741. 61741, because whatever the power we are getting, power available in bed, it should be always greater than 200 kilowatt. So from there we are getting 617.41 kilowatt. This is the final answer for this available power in the wind. Now coming to the next problem. So the next problem is that if the wind turbine operates at maximum power coefficient at rated wind speed. So it is given as that wind turbine is operating at maximum power coefficient at the rated wind speed. Then calculate the mechanical power extracted from wind. Then you have to find the maximum power extraction from the by the wind turbine. What the wind turbine fetch the power available in the wind. So this relation, as I discussed, so we can say that power extracted from wind. So you can also say that power extracted by wind turbine is related by power coefficient multiplied by this power available in the wind, Cp into P naught. So here we have to find this maximum power coefficient. It is operating at Cp max. So Pt will be Cp max into power available in the wind. P naught is what? Power available in the wind. So we all values know Cp max is given as 0.38, 0.38, and P naught we have calculated in the last problem, 617.41 kilowatt, 617.41. So on multiplication we will get 234.61 kilowatt. So yes, this value should be greater than 200 kilowatt. So we are getting that. If you are having doubt, then you can ask. Otherwise, we can move forward to the next problem. So the next problem is that calculate the combined gear generator efficiency eta. So for this, we know that what values we required for this. We are given this electrical power output, that is the synchronous generated power output. So it is denoted by PEL. So electrical power output is given as 200 kilowatt, and we also know that power extracted by the wind turbine, power extracted by wind turbine, PT is given as 234.61 kilowatt. We know that electrical power output is the combined gear generator efficiency into PT. So from here we can find this efficiency. So electrical efficiency will be electrical power output divided by PT. Combined gear generator efficiency electrical power output is 200 kilowatt divided by 234.61. So it will be 0.85245 or 85.245%. So for this we get the answer C. So how many of you are able to solve this problem? C is the correct choice. Pedro and Jignesh, both of you can try the problem. Moving forward to the next problem. This is 15th number problem. So in this problem we are given as it tells that find the required diameter of a wind turbine to generate 4 kilowatt at a wind speed of 7 meter per second. So 4 kilowatt is the output of the output of from the wind energy conversion system, and the wind speed of 7 meter per second is given and rotor speed of 120 rpm. Assume power coefficient as 0.4, efficiency of mechanical transmission 0.9, efficiency of generator is given 0.95, air density is 1.25 kg per meter cube. So you need to apply this final electrical power output formula. So what are the values we are having given? Mechanical transfer efficiency. It is also called a drivetrain efficiency or gearbox efficiency. So all in different ways it is given. Mechanical transmission efficiency is given as 0.9. So somewhere you can also see that it is drivetrain efficiency, or somewhere you can also see that gearbox efficiency. Gearbox efficiency, generator efficiency is given as 0.95. Air density we are given as 1.25 kg per meter cube, and power coefficient means Cp is given as zero point 0.4, and electrical power output is given as 4000 watt. So we know that electrical power output is efficiency into PT. We know this, and further we bifurcate electrical power output will be efficiency into Cp into P naught. Further we can also write electrical power output is equal to N efficiency combined efficiency Cp into half rho A U naught Q. So putting all these values, electrical power output is 4000 watt. Combined efficiency we have to put, so it is 0.9 mechanical transverse gearbox efficiency, generator efficiency is 0.95, Cp is 0.4 into half, rho is 1.25 kg per meter cube, area is pi into r square, so we can say that d by 2 whole square, and then u naught is equal to 7 power q. So this expression comes as, so finally we can write the d expression. So d expression will be 4000 into 2 into 4, and this d by 2, so 4 comes that side, divided by 0.9 into 0.95 into 0.4 into 1.25 into pi into 7 power q. So doing all this simplification, d will be under root of 69.4656, so 8.3346 meter. So correct answer will be B, 8.33 meter. So how many of you are able to solve this problem? Petro engineers. Just you need to remember this expression, and you have to apply all these carefully, all these terms carefully. Then you can able to solve problems very easily. The next problem is that it is also based on wind energy conversion system. So it is given as a three-phase 10 kVA a squirrel cage induction generator is driven by a fixed pitch angle wind turbine. The generator delivers its rated power output at a wind speed of 12 meter per second. The generator is connected to an infinite bus. The line-to-line voltage at the infinite bus is 208 volt. The generator is driven at rated wind speed. So it is driven at the rated wind speed So it is 12 meter per second, delivering its output at a lagging power factor of 0. 0.8. So calculate the active power output. So we are having given as apparent power rating. We can easily calculate the electrical power output. Squirrel cage induction generator is of rating 10 kVA, and then power factor is given as 0. 0.8. And what will be the electrical power output? Electrical power output P electrical is given as S into cos phi. So 10 into 0. 0.8. So 80 kilowatt is the electrical power output. Sorry, 8 kilowatt is the answer. So A is the correct answer. The active power output from this squirrel cage induction generator. Petro, I think Jignesh left. Petro, you can try. We are having 4 more questions, and after that we will stop. These are having very simple problems. Now the next problem is that calculate the generator output current. For calculating the output current, we are having power, voltage, and this power factor. You can calculate. So we are having given line to line voltage, VL is 208 volt, and this electrical power we have calculated as 8 kilowatt. Cos phi power factor is 0. 0.8. Then from here we can write that electrical power output will be root 3 times VL IL cos phi. So electrical power output is 8000 watt is equal to root 3 into line to line voltage into IL cos phi 0. 0.8. So from here you can get the IL value as 27.78 ampere. Another way you can also find this current from this apparent power rating. So we know that AC is equal to root 3 into IL. AC is given as 10 kVA. So 10,000 root 3 VL is given as 208 IL. Then we will get IL we will get 27.78 ampere. Either way you can approach. So for this problem, D is the correct answer. Pedro, if you feel face any doubt, if you face any difficulty in solving, then you can ask. You can type in chat box also. I can see that. Now here we have to calculate the reactive power the generator needs. Simply we already found out this current. From there we can find out this Q. So we require this sine phi. So if cos phi is given as 0 0.8, then by default it is already so many times used. So sine phi will be 0 0.6. So it is very useful for to just remember these two terms. So we have to find this electrical power output, reactive power the generator needs. So Q electric will be root 3 VL IL sine phi. So root 3 times VL is 208, IL is 27.78, sine phi 0.6. So finally you will get 6000.48 var. So it will be 6 kVAR. If you see the options, C option is correct, 6 kVAR. Now let us see this problem. This is the problem based on this common data only, and the last problem for this common data. So in this problem it is asked that the wind speed drop to 8 millimeter per second. So it is operating, the earlier wind turbine is operating at the wind speed of 12 meter per second. That is rated speed. So now this wind speed drop to 8 meter per second. The generator efficiency stayed the same. Generator efficiency remains same, but the aerodynamic coefficient becomes 80% of what it was. So aerodynamic coefficient remains means that Cp. It is denoting Cp. That is power coefficient. So this drop to 80% of what it was. Calculate the power output of generator. So we know that electrical power output is efficiency into Pt, and this electrical power output will be Pt if we explore then further write in terms of Cp and P naught, then Cp into half rho A U naught Q. So in this EBC the power output generator, then two terms are changing. This Cp is changing and this U naught is changing. So we can say that P electrical is directly proportional to Cp and U naught Q, right? Then we are having, so if we write in ratio term P electrical 1 divided by P electrical 2, then it will be Cp1 into mu1 Q divided by Cp2 into mu naught 2Q. And let us take this Cp1 as Cp and then Cp2 80% dropped. So it becomes 80% what it was earlier. So Cp2 will be 0.8 into Cp. And other one terms are like U01 is given as 12 meter per second. and u02 is given as 8 meter per second. So from there you can find this P electrical 2, and P electrical 1 we also know that we have calculated that comes as 8000 watt. So now it becomes simpler. All terms are we are given. So 8000 divided by P electrical 2, Cp1 is Cp, mu1 mu01 is 12 meter per 12 ka cube, then Cp2 is 0.8 into Cp, and u02 is 8 by power q, then Cp will get cancelled out. So finally P electrical 2 will be 8000 into 0.8 into 8 by power q divided by 12 by power q. So you will get this value as, sorry, so you get this value as 1896.3 watt. So it is approximately equal to 1.9 kilowatt. So A is the correct answer. So you can see the difference. If you are reducing this wind speed to 8 meter per second and aerodynamic coefficient 80%, how less we are getting the electrical power output. Earlier we are getting 8 kilowatt, and now we are getting 1.9 kilowatt. I hope you are able to get this problem. This is nice problem. I hope you all are able to get this question, able to understand this question. Now we will solve the last problem of today's session, that is problem number 20. So this problem based on the tip speed ratio. So this problem is that a 40 meter diameter 3-bladed wind turbine produces 700 kilowatt at a wind speed of 14 meter per second. Diameter of wind turbine given as 40 meter, 3-bladed turbine it is having. So and produces 700 kilowatt at a wind speed of 14 meter per second. The air density is 1.225 kg per meter cube. Find the rotational speed of the rotor at a tip speed ratio of 5.0. So we have to find the rotational speed. So we know that tip speed ratio TSR or lambda, it is denoted as lambda, is the ratio of tangential wind speed divided by the rotor speed. Tangential speed of rotor divided by wind speed. Tangential speed is r omega, wind speed is u naught. So lambda is equal to r omega divided by u naught. This is very important. All of you kindly remember this problem. Remember this expression, and omega we can write in rpm, then 2 pi n divided by 60. So here rotational speed in radian per second, and this n is rotational speed in rpm. Putting all these, we are having r into 2 pi n divided by 60 u naught. So put all these value. Lambda is given as 5.0 and r is given as r 40-meter diameter. So r will be 20 into 2 pi, n is unknown, and divided by 60 into u naught. U naught is 40 meter per second. So finally we'll get n is equal to 7 into 15 divided by 5 pi. So 105 divided by pi. So we will get 33.42 rpm is the answer. So correct answer will be B, 33.42 rpm. Pedro, I hope you are able to get this problem. So that's all about today this session. Thank you for attending this session, especially Pedro, who is the only attendee. So we will meet in the next session. That will be revision session, because this session is for assignment number 12, and next session will be, that will be last session, and in that session we will just revise all the express, means we will see all means starting from all tutorial session, what are the important points, what things we have to remember for the final exam. So that will be very beneficial for the final exam. We will revise all the tutorials in the next on the next Saturday, and hope you all will attend. So thank you, Pedro, for attending this session. Okay, bye.